welcome everyone. So we're gonna get started. We're gonna start off with just a few introductions. So we've got a few people helping out today, and a bit of administration. There's biscuits to help yourself on every single table. And if you want to try different biscuits, feel free to go around to the other tables. We have plenty of breaks, so you can have that. And then when you have the coffee, you can eat them. There's the penguins there, which are actually really good with coffee. So I do recommend the penguins with the coffee. So we're going to start today, and we've got this video here just to kind of get you in kind of the mindset of the OHDSI patient prediction journey. So we're going to go through the different aspects of the OHDSI framework for patient prediction, how to think about a prediction task that's clinically useful, how to actually develop a model design using best practices, and then you're going to have some hands-on experience of actually using an R package to develop a model, using some data sets you can actually explore the results of that model. And then there's going to be some exercises for you for that. So there's a few faculty members in here today. So we've got Egill, who's going to be doing the live coding. We've got Chung-Soo, who's going to be explaining the way to think about a prediction task and what patient prediction is. We've got Mitch, who's going to be helping with all the exercises, and he's our expert in phenotyping. So you're going to, when you're thinking about your prediction task, he's the person to ask for the phenotypes. We've got Young, who's going to be joining later on in this session. He's going to be talking about federated learning. And then I'll be going through the patient prediction framework and some best practices. So the agenda today is, we're already at the point where we're about to start what is patient prediction. And you see we've got about 3 different 30-minute presentations followed by exercises, and there's plenty of breaks. So you're going to have a break roughly every hour where you can have coffee and biscuits, and we'll be able to go around and help with the exercises. So at that, I'll hand you over for Chung-Soo, who's going to explain what patient prediction is.
Hi, everyone. I hope you guys have a great lunch. This is Chung-Soo. I'm a postdoc associate from Yale University. I'm really glad to have this session. Today, I want to talk about before we're going to start, I'd like to just remind you the OHDSI missions again. So OHDSI missions is to improve health by empowering a community to collaboratively generate the evidence that promotes better health decision and better care. The cool thing is that we've got this amazing community, so where we can share, collaborate, and we can learn from each other, so including this tutorial as well. So, okay. I put the key topics to cover these 30-minute sessions. So the first thing we have to get in our mind after this session is that what is the prediction versus other OHDSI analysis, and then why is the prediction is important, and what is the TAR, the components of the prediction task, and we can see some examples on prediction task and also prediction models, and finally we can deal with some other considerations briefly. As you already know, a lot of things happen to patients in real-world clinical care. They get diagnosis with their conditions, so go through tests and receive treatments and get prescriptions for their medication. And then this whole process can happen over multiple visits. And every patient ends up going through their own unique journey. So all of these events are captured as a data. And along the way, there are so many different questions we can ask about these patients' journey, actually. So maybe, for example, which treatment did patients choose after diagnosis, and which patients choose which treatment, and how many patients experience their outcome after treatment. So these questions related to describing patient characteristics. Maybe we can think about another set of questions we might have. What is the probability I will develop the disease? And what is the probability I will experience the outcomes? these are more like personalized and predictive in nature. Yet another set of questions includes, does this treatment cause outcomes? Or does one treatment cause the outcome more than alternative options? So these questions focus more on causal relationship. So these questions can be grouped into three main areas within the OHDSI framework. So first thing, clinical characterizations. That means what is happening to these patients, so which is observation. And the second is patient level prediction. So what will happen to me or what will happen to the patients, so which is the inference questions. And lastly, population level effect estimations. So what is the causal effect, which focus on to the causal inference. So in this tutorial, actually, we will focus only on the patient level prediction and inference part. So the other topics are being covered in the parallel tutorial. So if you are more interested in those session, then this is the last moment you can escape. So, okay, so no one, oh, there is someone. So clinicians are confronted with prediction questions on a daily basis, actually. So what options do they have? We can take this simple but powerful example. For example, a patient with AFib, atrial fibrillation. Maybe when patients ask us, what's my risk of having a stroke in the next year now that I have atrial fibrillations? When questions like that comes up, what can doctor really do? So first, doctor can deny ability to predict at individual level, just saying, oh, we cannot really predict your risk precisely. But it is not what patients want to hear. But sometimes it's the most truthful answer. The second we can think about on the answer is that just to quote in overall average to all the patients. For example, for people your age and gender, the risk is about like 15%. That's basically just summarizing data. Third, often doctor can rely on their knowledge and their own experience, but that's really tough job for human. Prediction usually isn't about one single factor, so it's about how multiple things come together. So very tricky part is knowing which factors are actually matter. Maybe in an ideal world, the doctor would provide a personalized prediction based on an advanced clinical prediction model, which take patient's whole medical history and gives a personalized risk estimate. Someone said prediction is very difficult, especially about the future. But we have some good news. We live in a time overflowing with data, and we have incredible computing power. So that means we have real chance to push this patient-level prediction forward in a way that weren't possible before. So that's why OHDSI has made patient-level prediction as one of big focus. So, and we think OHDSI is in a unique position to lead this space. There are several real-world examples on clinical prediction models. Following the case in the previous slide, we can think Chad-Best score model for atrial fibrillation stroke risk. The specific question for this model is that amongst patients newly diagnosed with atrial fibrillation, which patient will go on to have stroke within a year? This model is using age, sex, congestive heart failure history, hypertension, stroke, vascular disease, diabetes as a predictor. So for example, we can think about for a female with AFib, age 78 with a history of hypertension and vascular disease, then we can say the patient's risk of stroke is 7.2% in the next year. Another example on clinical prediction model is the PREVENT score, recently released by AHA and ACC. The specific question for this model is among its patients aged 30 to 79 without known cardiovascular disease before, which patients will go on to have total cardiovascular disease within 10 years. So this model is used because assessment of absolute risk of cardiovascular disease is recommended to guide primary prevention for CVD. For example, initiation of lipid-lowering therapy on basis on this estimated 10-year risk of ASCVD. So we can calculate the risk like for a male, age 34, without known cardiovascular disease, the patient's risk of total CVD is just 0.56% in 10 years. Actually, that is me. I think some of you may have already noticed that I keep talking about a specific question for the clinical prediction model. So every prediction model starts with its own specific question. So for the rest of this session, we are going to step back and think about how to ask the right question in the first place. So when we want to make a prediction, it really helps to define the problem in a structured way. So OHDSI is like to use a simple framework to define any prediction questions, like among a target population, we always say this is T, and we aim to predict which patients at a defined moment in time will experience some outcomes during at the time at risk. So within this framework, we can start to think about what each of the key parameters should be. So the first thing is the target cohort. So the target cohort is the group of patients we want to make predictions for, essentially our study populations. And then outcome cohort represent the specific events we are trying to predict. The time at risk define the time period over which our prediction will apply. So these are a key component to make our study clinical prediction task as a structured way. But beyond that, we will also need to decide which algorithm, parameters, and variables we will use to build the model. But we will cover that part in the next session. So for now, we are just focusing on the T, O, and TR. So we're gonna learn about the structured way to define the clinical prediction task. So now using this standardized prediction task question, what kind of question we can have? We can see some real world examples. In healthcare, there are many different types of prediction questions we might ask. So for example, we might want to predict some kind of disease onset or disease progression. And another common area is predicting treatment choice or treatment response. We could also ask some questions about treatment safety. And finally, we might be interested in predicting treatment adherence, whether a patient will stay on their therapy. So we're going to walk through one by one. So when we think about disease, to predict disease onset and progression, we can use simply structure like this. Among patients who are newly diagnosed with a certain disease, we call that is T, which patient will go on experience a specific event, which we call outcome, and O, and within a defined time period, which we are saying time at risk, TAR. For example, among newly diagnosed atrial fibrillation patients, which one will go to have an ischemic stroke in the next 3 years? Yeah, as we saw in the example before. And then when it comes to the treatment choice, we can frame our questions like this. Among patients with a certain disease, then who are treated with either treatment A or treatment B, which patients end up receiving treatment A on day 0. That is actually exactly the same definition by propensity score model. So, for example, among patients with atrial fibrillation who took either warfarin or rivaroxaban, which patients got warfarin, something like that. The next example is about the treatment response. So for treatment response, we can ask among patients who are new user of a certain disease, which patient will sum up response in the specific time window. So for example, we can think about these questions: which patient with type 2 diabetes who start metformin stay on the metformin after 3 years? And for the treatment safety, we can structure our question like this. Among patients who are new user of a certain disease, which patient will experience adverse events within a specific time period? So, for example, among new year of warfarin, which patient will have a GI bleed in 1 year? And lastly, we can think about clinical prediction tasks on the treatment adherence like this as a structured way among patients who are new user of a certain disease, which patient will achieve adherence metric at the specific time period. So we can structure our question like which patients with type 2 diabetes who start on metformin achieve over 80% of proportion of they covered at 1 year. So all of these questions and curiosity on the clinical prediction model mentioned before can be taken a step further by adding another layer as well. So, how do we choose? Okay, so how do we choose something that is really clinically meaningful with some point like, we should think about based on our previous structured question, and we may further think about is this question is really needed in the clinical practice? Is there a current medical decision you find difficult? Is there a clear point in time you can apply in a prediction model to help with decisions? Or is a target and outcome recorded in our data as well? And how common in outcome in our database or something like that? So it was very brief introduction on our patient level prediction. But I really wanted to say was that we can structure our clinical question in established patient level prediction framework. So, and then add some clinically useful and critical layer to crystallize our question. It's all about the questions. Yeah, so it was quick, but this is my session. So I hope this introduction will be some help in you thinking and organizing your important prediction question. Thank you. Any questions on No one followed? Okay.
So thank you very much. One question I have is about the way that you're defining the tasks here is, in some settings it's useful to include like a gap window to prevent future data leakage for certain tasks, where you say, oh, I want my outcome to occur within the time at risk, but not within a sufficient time after the sort of onset of the risk period, right? Like if you're predicting, mortality or something, you say, I don't want to count it if my patient dies within 10 minutes of the start of the limiter because it was probably very obvious. At the time of the prediction. Is there a way that this is sort of formalized, or is this sort of not something that's included in these sorts of tasks that you're looking at?
Is this working? Can people hear me? So yeah, so you're asking about a gap between the index and predicting the outcome. Yeah, so when you define your time at risk, you can specify like a gap to say, I'm not interested in the first 30 days after the target index. And that can make it more safe, because that way you're kind of separating your outcome a little bit more from your features that you're using. So yeah, you can add that gap in. We often haven't used the gap, but you could.
Thanks.
Oh.
So I guess one of the things that in using the PLP package I found very important is like the upstream phenotyping and being able to effectively select your cohorts, and that can have a huge impact on the performance of the models downstream. And I guess I wondered if you had any thoughts on kind of an iterative workflow or a standardized mechanism to update cohorts based on model performance, and like if there's kind of a process that should be followed. Maybe this will be covered in a later session, I don't know. But if you can just speak a little bit to that, the importance of that and the potential for using PLP to improve phenotyping potentially. Is that something that you think would be possible?
I don't think we have kind of framework to update our study populations based on the prediction results. Is that correct?
So yeah, we don't really have anything in place to improve the phenotypes from prediction, but I do find that when you do a prediction, often you'll see errors, if you have errors, in your outcome and target cohorts. So then, and that will force you to update it. So we don't really have a framework, but I think that when you develop a model, the errors are normally very clear in your, so like you'll see a code that you should have included in your outcome being predicted.
Oh, okay. So actually thank you. So actually we prepare some exercise on this session. We can just create our own prediction task based on my presentations. You can create your own clinical questions as a structured way following the TOTAR. So I think you guys already have a paper on your desk. Okay, yeah, Jenna. So you guys think about what is the interesting clinical prediction questions based on this structured way, and then you can discuss what is the suitable our study population as a T, and what is the best interesting outcomes as an O, and what is the time specific time point you want to predict as a TAR, time at risk. So, but you should keep in mind, will these patients you already said as a T will be identifiable in your data? And then is there a medical question this can aid as well? And then is there an intervention this can help? So let's start. This one? This one? Okay. So if you have any question and need some clarification, just let us know. There are some PLP helpers are here.
I went around and I heard everyone's prediction tasks, and I thought that we'd come up with a lot of great tasks. And what I really like is that people were thinking about making sure it was clinically meaningful, and everyone had that clear index, which is going to be something that you'll see a lot in the next few slides. So we already had our break. So now I'm just going to go through the actual framework that we have and some of the best practices that we've learned through this, applying this framework at scale on the OHDSI network. So there's a lot of model design choices that when we started 8 years or so ago, we didn't actually know the answers, and we did research to answer those questions. So the patient-level prediction framework, it's a publication that we had in 2018 that explains how you go from the OMOP CDM to extracting the data, the labeled data, learning a model, and actually evaluating the model in a standardized way, and actually being able to generate a model that you can share and do external validation at scale as well. We also have an R package that will implement that framework that's maintained by AIC, and he also has a deep patient-level prediction package as well. So you can do lots of different models with those two packages. Now I'm just going to go through this slide briefly, but this is the general process that the framework implements. And the first part is the data extraction. The key thing for that is your prediction task. So that's why we did this exercise earlier, where you think about what is your target population, your outcome, your time at risk. Those are the key components that will take you from the OMOP CDM to the labeled data that we're going to use to learn. And then we're going to go through the different steps to process the data. So you get the labels, you process it in some way, fit the model, and then have some standardized evaluation. These functions that you see on the right, you don't worry about them, remembering them, but I put them here because when you do the code with AIC, these are some of the functions you might see, and I just wanted to show you on here where they correspond to, so you can go back to this slide and see, oh, this is how it fits into the framework. So the first part of developing a model is extracting your labeled data. So you've got your OMOP CDM data. You need to generally have some rectangle data that is labeled that you can use to learn your model. So many of you are probably aware of the OMOP CDM. This is all the different tables that you have in the OMOP CDM. So you start off the main one, which is the person table. So this has information that's like identifier for a person. It tells you whether they're male or female, their year of birth. Sometimes you have race, and you have some information about their location. So you have this for all the people, and each row is a person in your database. Then you have information about when they're observed in the data, if they have any death record, if they have any visits, and you have information about conditions, drugs, procedures, devices. And these tables are the key ones we're going to be using. And this actually is just time or date stamped entries. So for each person in your database, you will have multiple rows generally that gives you some code that will correspond to some medical condition. This code could be diabetes, for example. And then you know when they started that and when they ended that. So this is the condition table, but we have these date stamped entries for drugs, procedures. So effectively, we just have temporal data for each person in our database. And we need to take that and convert it to the label data for our prediction task of interest. So this is what we actually need when we do a prediction. So for our task of interest, we need to create this data set where we know all the people in our target population. We know whether they had the outcome during the time at risk. Yes means they had the outcome, no means they don't. And then we need some features that describe those patients. So what was their age at index? Were they male or female? What history or condition history do they have? What are they currently having? What drugs did they take recently? What drugs did they take in the past? So we need to have code that goes from the OMOP CDM to this data. And we have a standardized process. As long as you know your target cohort, your outcome, and your time at risk, we have a process for extracting this data in a very transparent and clear way. You also generally think about other data inclusion criteria. So you may think about Do you only want to extract people from 2010 onwards, so more recent data? Do you want to remove people who had the outcome prior? So there are some other inclusion criteria that you might want to add that you didn't put in your target cohort, but you want to include or exclude these people when you extract the data. And then you also need to think about what features you want. So the features are actually the key part of the prediction. If you have bad features, you're not going to have a good model. If you have really good features, you'll be able to get a better model. So you want to think about what features as well would you want to include. We have a library of features that you can select. So we will actually have features that say you can actually look at any condition that a patient had in their last 30 days, last year, any time prior. You can look at any drug that someone had in their last 30 days, year prior. So we have lots of different features you can select from, and you can actually create your own features as well. So when we extract the data, we use a retrospective cohort design. And the way it works is you specify your target, your outcome. You also need your target index, as I kind of stressed to everyone when I went through the exercises, and your time at risk. And what we do is we find people in the target cohort, and this will generally be done through a phenotype. So if you haven't heard the word phenotype before, there's lots of information on OHDSI about creating phenotypes for cohorts of interest. And we will have their index, so when they entered the target cohort. So if the target cohort was new users or people newly diagnosed with diabetes, the index would be the first time we see diabetes for that person in the database. And we're going to use records prior to index to create features. And we're going to look at some time period post-index, which is our time at risk, to see whether they have the outcome or not. If they're in the outcome cohort during this time period, after the index, we're going to class them as they had the outcome. If they're not in the outcome cohort, we're going to class them as they didn't have the outcome. So we use a retrospective cohort design because it's very clear what the task is. The target, the outcome, and the time at risk specify this. There's a clear index. And this is important because the index that you use in this retrospective design is also the index you'll use clinically. So in the example, I mentioned the first time we see diabetes in the data as our index when we're extracting the data. This is when you would apply the model clinically. As soon as someone's diagnosed with diabetes, this model can be applied to them. So we have a very clear point in time where you would implement the model, and that's when this model has been validated, and you're going to actually be able to make sure that model works at that point in time. We also get this separation where we're using data prior to create the features, and we're using data post to see whether they have the outcome. So we have less likely to have issues. I say no issues, but we're less likely to have issues with the outcome being used as a predictor. And if you have a bad design, that's not guaranteed. I've seen outcomes be predictive of the outcome. So we actually have a paper where we looked at this design versus a case control design. And if you're interested in reading more, you can go to this paper. But in summary, the case control design, it pivots on whether you have the outcome or not. And it will look at the prediction indexes sometime prior to the outcome. But when you're applying a model, you don't know who's had the outcome, when they're going to get the outcome. So when would that time period be? You don't know. So a case control, there's a problem of like the index of when you apply a model isn't very clear. So we propose that you shouldn't use a case control. Pretty much every prediction task can be written as a cohort design, and it should be. So once you've got your data extracted, the next thing is actually to split into test, train, and validation data. In the framework that we have, if you imagine this top rectangle is the full labeled data, what we recommend is you split part of that into training data, and this is used to develop a model, and you're going to use some that you hold out as your testing data. Now, when you fit a model, most model will have something called hyperparameters, and these affect the learning process, and they can actually affect like the complexity of a model. You have to learn those for your prediction task, and one way of doing that efficiently is to use cross-validation, where you do your training set is also your validation data used to validate the hyperparameters. So we use something called a training set, a test set, and then we use cross-validation in the training, where with the training data you split it into n unique partitions, and these are all disjoint, so it's different people, different data points in each of these folds, and we use n-1 of these folds to evaluate the hyperparameters, or to develop the model, and then use the last fold to evaluate the model. You do this for you leave every fold out once. You calculate the average of whatever metric you're evaluating, and then that will give you an estimate of how well the hyperparameters did. You pick the best hyperparameters, and then you fit on all the training data. So that's the process that the framework will do. By default, we recommend that you do 25% in the test set and 75% of your data in the training, but this will vary depending on how much data you have. So there's been some studies to investigate this. You'll see there's lots of papers that recommend you use bootstrapping to evaluate a model internally. But this is if you have small data generally. If you have big data, bootstrapping actually is pretty hard to do. So in big data, we actually did a study and we investigated actually what is the best strategy. And we found that it doesn't really make too much of a difference how many folds you have. So we recommend using 3 folds. And as long as you have big data, a 25% test set is sufficient. So our framework assumes you have big data, and for your exercises you're going to be doing next, assume you have big data when you're designing your split. I do want to point out that when we do this split, we do make it stratified on outcomes, so the outcome rate is the same in the training and the testing. There are other splits you can do, so you can actually do a split. So the default is the outcome stratified, but you can also do a split on time, where you say I want the most recent data for the testing and older data for the training. And that can kind of give you some information if there's temporal shift in the data. So once you've done your split, the next is actually doing the data processing. Now, I put this in, the class imbalance. This is a common topic in machine learning, and I see it's a very common topic when you're developing prediction models of whether you should balance the classes. So most healthcare tasks, and pretty much every healthcare task that I've been investigating prediction models for, there's a big imbalance where the outcome is much rarer than the non-outcome. And there's this conception, or this kind of misconception, I'd say, that you should always balance. And that has some elements of truth. So the machine learning algorithms generally will learn better because of the objective functions they have when you have balanced classes. But in reality, we have an imbalance in our application data. So when you're applying these models, the outcome is rare. And if you balance, there's been numerous studies that have shown that you actually will create a model that's miscalibrated. So we recommend that you shouldn't do any sort of balancing in general. These studies investigate very basic balancing methods. And I'm not saying that there isn't some methodology for balancing that could do much better, but for the basic methods out there, they generally cause calibration issues and they didn't improve discrimination. So you'll see this is actually in red because it's part of the framework. You can put in a balancing method, but we actually recommend you don't. Then there's the feature processing. So this is feature engineering, feature selection, and pre-processing. In the framework, you can plug in your own functions to do any feature engineering. So if you extracted age, but you wanted age squared, you can create a function that will create that age squared or log age, and that will be feature engineering. So you can do any methodology you want of feature engineering, but you generally will have to write your own R code at the moment. We don't have a very big library for feature engineering at the moment. There's also feature selection you could do. So again, you could create your own method for doing feature selection and put that into the framework. The pre-processing, we do have a standard function for that. And the pre-processing will scale the features between 0 and 1. This is often needed for things like logistic regression. You should be doing this. And then it will also remove redundant features. So if you have a feature for male and female, most of our data sets, they're the only options. So you can remove one of them. And then it will also have the option you can remove very rare features. Our way of extracting the features, we often end up with 20,000 plus features. A lot of them will be very, very rare. And you may just want to get rid of them because they're just going to slow down the model training and they're not really going to be useful. So that is, these are functions that you can set and some options in the design you can specify. Now the model fitting. So once you've got your label data, you've processed it, now you need to actually fit the model. I wanted to just have this slide here just to give a very, very brief overview of what happens when you fit a prediction model. So the easiest way to visualize this, I find, is think about two feature space. So covariate 1, also known as feature 1 here, covariate 2, also known as feature 2 here on the y-axis. Each dot is a person, If they're an X, it means they have the outcome. So for this person here, they had a covariate value of whatever would correspond here, so maybe this is 10, and they have a covariate 2 value of something here, which is quite high. So this is just the two-dimensional, two features. X is they had the outcome, 0 means they didn't have the outcome. When you're fitting a model, what you're trying to do is partition the feature space into areas that are mostly people who are going to have the outcome and mostly people who aren't going to have the outcome. So if you had a linear model, for example, your decision boundary, you may put it here. What this is going to do is now this model is going to say anyone who has a new value, so if their covariate value 1 is up here and the covariate value 2 is over here, and they fall above the line, we're going to predict them as a no outcome because there's mostly no outcome people here. But you can see we're underfitting. We're going to actually have some outcome people incorrectly predicted with this linear model. And if they fall in this region down here, we're going to predict them as being a no outcome person. And probably fairly accurately if this, we don't have too much data, but that's not terrible. So this is basically how you fit a model. It's just fitting a function to partition the space, and then you're generalizing this so that new data points, you can basically look at this decision boundary and see where it falls. And you have this thing called underfitting, and underfitting means that your model is not complex enough to be able to do a good decision boundary. You've got overfitting, where your model is so complex, it can perfectly partition out the label data you have, but it's actually prone to fitting basically noise. And there's probably some points around here that you might actually get incorrect because it's kind of like fitted to this data point too much. And then you've got something where you don't overfit, you're just about right, and this was probably going to get you the best model. So when you do the model fitting, basically we've got algorithms that will do this for you, but this is what it's effectively doing, is learning that decision boundary. Now you can see that based on the decision boundary, the classifier that you want to fit, there's no algorithm that's always going to do best because it really just depends on what the data looks like in the space. But we have a library of classifiers that you can pick from. So the one that we've used a lot is the regularized, the lasso logistic regression. We also have random forest, gradient boosted machines, naive Bayes decision tree, ADA boost. We have the deep learning, the AIC has in the deep patient level prediction. And you can add whatever classifier you want in here as well. So we've made it very flexible in the framework that you can add in your own classifier. And you can select as many models as you want to fit for your prediction task or for your data you've got extracted out. And if you have no time constraint, the best practice is try lots of classifiers. You never know which one's going to do best. The next thing I'm just going to talk about how we evaluate the models. So there's two key overall performance metrics that people will investigate when they develop a model. The first is the discrimination. And this is just saying, are you assigning a higher risk to people who are going to have the outcome and a lower risk to people who aren't going to have the outcome? The most common metric that's used is the AUROC, the area under this curve, basically. If it's a value of 0.5, it means that you're just randomly assigning risk to people. You're just making up a number when you see someone. If you've got an AUROC of 1, it means you've got perfect discrimination. Everyone who has the outcome has a higher risk. Everyone who doesn't have the outcome has a lower risk. So the higher your AUROC is, the better. Generally, an AUC of around 0.7 to 0.8 is what we often see for models that do pretty well in our type of data. If it's too high, it's probably suspicious. And then you have this visualization as well. So the random classifier is on the diagonal, and the furthest away you are from the diagonal, the better your model. So these are the key things that people present when they do a model. And then there was a lot of papers about how calibration was being forgot. So calibration is the prediction that it's assigning you correct? Is it accurate? So if you had 10 people and they're all assigned a 10% risk, you'd expect one of them to have the outcome if the model's well calibrated. If there's more people that have the risk, then your model is underestimating. If there's less people that have the outcome in the 10% risk, then your model is overestimating. So calibration is very key, especially if you're going to be applying the model. If you're going to be using the model to guide an intervention, you want it to be calibrated well. And the metric we use is the calibration in the large. So the calibration in the large, you look at the mean predicted risk and the observed risk. And if they're close in value, it means overall you seem to be calibrated pretty well. We also have plots where if you ranked everyone by their risk and you split them into 10 groups, You then calculate the mean predicted risk in each group and the observed risk in each group, and that it falls on a plot here. So you've got the predicted probability here and the observed probability here. And if it falls on the diagonal, then it's well calibrated. If it's below or above, then it's miscalibrated. So these are the overall performance metrics. But when you're applying a model for a clinical question, you also want to look at the threshold-based metrics. So the threshold-based metrics, you say, if you have a predicted risk greater than some threshold, I'm going to say you are positive for having the outcome. Otherwise, you're negative for having the outcome. And you're going to give the intervention to people if they're positive. You want to make sure that your performance is good enough if you're going to be using this for some intervention. So if you, for example, had a threshold of 10% and someone was predicted 12%, they're positive, they'll have the intervention. If someone has a predicted risk of 8% with a 10% threshold, they're negative, they won't have the intervention. So you want to look at the predicted negative, predicted positive against the true positive, true negative. If you predict a positive and they are positive, they're true positive. If you predict they're positive and they're actually a negative, they're a false positive. If you predict they're a negative and they're actually a positive, it's a false negative. And if you predict they're a negative and they are a negative, it's a true negative. And then the two key metrics really are sensitivity. So this is actually how many of the people who are positive is your model going to correctly identify and give the intervention. And then there's the precision, and this is if your model is saying people will have the outcome, how many of them actually will go on to have the outcome? And you often find that with rare outcomes, your precision is pretty low, and that actually is going to impact how useful a model is. So this is actually a very key metric that I think often gets somewhat ignored. Oh, and I just want to clarify on the last slide, best practice, always make sure you add confidence intervals around your AUROC. You're pretty much going to get told to do that in a paper if you don't do that. So we've got these evaluation metrics. How do we actually apply them? Well, we saw at the beginning that we do this split into we have this test holdout. We have labels for those people. We just never use them to develop the model. So imagine this is our people, some of the people we had who weren't used to develop the model, but we know the ground truth. We then apply the model to those people, and we get the prediction, and we can then compare the prediction with the true outcome to basically do that overall performance and also the threshold performance, so we can actually get the internal validation using the test set. But with OHDSI, the nice thing is it's very easy to share models across the OHDSI network. So you can train your model and develop in one database. You can get your model, and then you can apply it very easily to any other database in the OMOP CDM, because the code that we use to extract the data is the same for every single database. So we can easily extract the data, we can apply the model, we can get the performances. So we can do external validation very readily in OHDSI, and that's a strength. But there's been a lot of talk recently in the prediction field that you don't necessarily always need to do external validation. If you're going to be applying a model to the database that you're developing it in, external validation probably isn't as important. But if you want to develop a generic model, you saw Chung-Soo gave you some examples of online forms where they had the models, and this is generic, it's anyone can go to that form and apply it. Then I would argue external validation is still important to make sure it works in general. And that's where you can validate. And you can validate other models developed outside of OHDSI, outside this framework. You can still use this framework to do external validation. And then finally, making sure that you actually share your models. There's a guideline called Tripod that we use whenever we publish models that will actually tell you what you should include in a publication. So if you develop a model and you want to publish this model, make sure to check out Tripod. Look at the statement, see what you should include as a bare minimum. There's a few things that I want to really highlight. I think it's very important that you should share the full model details for transparency. It should be very clear what someone did when they developed the model. It makes it so that other people can apply the model. It is crazy how often people publish models and there's something missing that you can't then replicate that model. And there's things like the intercept might be missing, or the survival, baseline survival might be missing. So make sure if you do this, make sure the model is available for people, and make sure all the code is there as well. So it's very transparent what you did, and people can fairly evaluate the model. It's crazy how bad this is kind of been followed, and how difficult it is to actually validate models because of that. So at that, any questions?
Thank you so much for the presentation. So my first question would be, how do you deal with the missing values?
That's a great question. So that's the number one question we get from reviewers as well. So I didn't really talk too much. So the question was about how to deal with missing values. The way we construct features, we use a package called feature extraction. The feature extraction feature is, did you have this code during this period of time prior to index? So the way we create the feature, you don't really have missing values, because if you don't have the code, because it's missing, you just treat it as you didn't have the code. So in feature extraction, we don't really have the missing issue. And then age and sex is always there. However, if you were to create custom features where you had measurements, then you would have to create some way of addressing the missingness. We don't have anything in the framework right now for doing the missingness. Well, actually, have you added it?
Yeah, it's been added. So now you can do like simple imputations like mean or median imputation on measurement values. And there is a experimental like iterative approach where you use the non-missing data to predict the missing data. It's similar to how mice does it, but it's not like, or like the iterative imputer in scikit-learn, if you're familiar with that. So that's recently been added to the package. It's marked as experimental. So if you use it, you'll get a warning. This is experimental, but I'd encourage everyone to try though. So.
One more question, sorry. So you mentioned rare features. So how rare does a feature have to be before you would drop it? Is there a threshold or a percentage that you would consider for a rare feature?
Yes, that's a really great question. So the way the framework works, I think by default, it's like 1 in 1,000. So if the feature is less than 1 in 1,000 people have the feature, it will get dropped. I'm not sure if I like that threshold, if I'm honest. So I think it depends on if I have very big data, I may be tempted to just not even use that, because it doesn't, if you have a very rare outcome, a feature that's perfectly predictive of the outcome would also be very rare. So I do worry sometimes whether we're dropping those really predictive features because they're rare and the outcome is rare. So if I have big data, I'm probably less likely to apply that kind of cutoff, because the model's got more data, so it's probably less likely to overfit. But in general, the default is 1 in 1,000. And I would recommend playing around with that. So when you do the exercise with AIC, try 1 in 1,000, try getting it to 0 and see how much of a difference that makes. But yeah, that's a great question.
Thank you.
So you commented on the difference between cohort design and case control design. So I guess my question is, for certain tasks, your sort of outcome definition will inherently be conditional on some aspect of the future, or potentially, or maybe it should be, like if you want to exclude patients who might be omitted from the outcome window because they left the data set from a censoring perspective or something like this. So what's your strategy for dealing with these sorts of like future constraints and how that impacts the model?
So I'm really glad you asked that, actually. That's a really good question as well. I'm getting some really good questions. So I think anytime you want to do an exclusion from the future, you have to be very careful, because you can compromise the generalizability. So we actually did a study where we looked at the impact of like loss to follow-up. And we originally, and I think it may still be in the framework, the default was if you were lost to follow-up, you were ignored, because you don't know the true label. If you're saying time risk of 1 year and someone's only followed for 30 days, you don't know what would have happened to them after that. So we were like, remove them because they're noisy. Then we realized it caused a big bias, because what we were doing caused a big bias, because we kept the people in if they had the outcome before their loss to exposure, because we knew that they were outcome. We were excluding people who didn't have the outcome if they were lost to follow-up. And it caused a really big bias and a calibration issue. So it actually shifted us to say, don't exclude people, like just accept that there's going to be some noise. Maybe do a survivor model instead. So the research shows that you've got to be very careful about how you handle that loss to follow-up, because you can be very easily cause a generalizability issue. Hopefully that answers.
Thanks for a great presentation. I wonder if you could touch a little bit more on the class imbalance issue. I was surprised, I guess, to hear you say don't adjust for it. Are there ramifications for not adjusting for it?
Yeah, so I think most of the machine learning algorithms in theory should do better if they're balanced classes. Their objective functions are kind of have the assumption that the classes are balanced. So the machine learning algorithms should do better. But are you're nodding your head, would you?
Oh, sorry, I'm not convinced of that.
Oh, yeah. So we're not even convincingly they should. But the problem is that I think the idea of doing the balance used to come from the idea that it was difficult to collect outcome data. So you could get non-outcomes more readily than outcomes. And then the reality was that there wasn't an imbalance. It was just the collection process caused the imbalance. And in that situation, you wanted balance because that's reality. But because our reality is imbalance, when you balance, it just causes way more issues that, like, the algorithms still do pretty well to fit the model, and you still get good discrimination in the imbalance setting. And when you balance, you're just causing a calibration issue. So the study, it was actually a study that Cynthia did from Erasmus, and she looked at real-world data. She looked at oversampling and undersampling, so very basic balancing methods. But she showed that the discrimination didn't change. So whether she balanced or not, the discrimination was the same, but the calibration and the balance data was terrible. And what I find really funny is a lot of publications will balance, and then they'll show them the performance in a balanced test set. And then their precision looks really good because they balanced. So it can be very misleading, and actually it can make their model look really great when in reality it probably isn't as good.
Great, thank you.
Hi there. A quick question about you mentioned there are certain arguments against externally validating algorithms right now. I was wondering if you could elaborate further on it. What are the arguments? What's the arguments against that?
Yeah, so we kind of, when we started doing Odyssey, we kind of pushed that everyone should do external validation. You can use our network to do external validation. So we were very much everyone should do external validation. And it's definitely had a shift that's kind of made me a little bit more careful about recommending that. So the idea is that some people believe that if you have the same, so if you have a database and you're developing a model in that database and you're going to apply the model in that database, it doesn't matter how well that model does outside that database. You should really just do a temporal validation to make sure the model still does well over time. And even if in some other external data sets it does poorly, should you not, if the model had an AUC of 0.9 where you want to apply it, and it's consistently doing 0.9 where you want to apply it for AUC, but it's performing 0.5 in a different database and you don't really know why, you shouldn't really stop using it, is kind of like the thought. But if you want a generic model, so if you want a model that's not going to be applied to that database, that's when I think the external validation is more important. So that's the argument, is that people are saying it's hard to interpret external validation, and it doesn't, if you can show it works, who cares? If you can show it works where you want to apply it, who cares what another database is how the other database is performing? Any other questions? If not, so the next part is actually going to be now using what I kind of presented to try and design your own prediction model for your prediction task. So same groups, we're going to hand out a new form, and in here you're going to be thinking about, is there any restriction you want to apply to your target cohort? What features do you want to include in your model? Any feature engineering you want to do, any pre-processing? And you'll be able to use this to feed directly into the implementation that you'll see Egill run. So you'll be running an example with him, but then in your own time, if you want, you could actually fill in the model design with these settings for your specific task. So we have 25 minutes, I believe, for that now. So Chung-Soo's going to bring around the forms, and then we'll do similar to the previous exercise where we'll come around and we'll chat and help. And if you have questions, feel free to kind of get our attention. Thank you for listening.
So it's good, like if you're going to follow along, you need to have R, and maybe someone at your table has R, and you can maybe group together. But there is a tutorial website So if you go to odyssey.github.io/tutorial-PLP, like you can see here on the screen, that's the quarter document for the tutorial. And it has instructions for everything. And I'm going to just go through it to start with, and then there will be exercises at the end where you can customize the pipeline we run. And yeah, let's get started. I'm gonna just change the mirroring settings a bit first. Okay, I hope everyone sees this. And I have a USB stick here with the example database if you don't want to download it. It's in the instructions to download it, but it's like 4.6 gigabytes. So we might spare the internet here a bit by passing this USB stick. And it also has the cohorts and the R script that we're going to run. So maybe Jenna can get this started to pass this around. So in this tutorial, we are going to load the cohort JSONs and generate the cohorts using cohort generator. We're going to configure a patient level prediction design, and we're going to assemble this into something called the Strategos analysis specification. So Strategos is a package that wraps around OHDSI packages, and it usually involves creating a JSON specification you can pass around, and then other people can run your code exactly. And then we're going to execute this against the DuckDB Synthia example database that is making its rounds now. So first, we need to set up our environment. You need to have R installed. You need to usually to run OHDSI R packages, you need Java, because there are some of the packages in the ecosystem that use Java. And some of the packages are only available in GitHub, not CRAN, so usually you need a GitHub account. So I'm going to assume most of you did this. If not, you can do it now. It should just take a few minutes. And then there is a few packages that we need that you can install with install packages. And yeah. So I'm just going to start So in the first step here, you can download the zip file that has the R script and the cohorts. And I assume then you have gotten this, download the zip file, extracted it in a folder, and opened the R script in RStudio. So I hope everyone can see my RStudio now. And you should have this networkstudy.r is the R script. And yes.
The argument is a little bit harder to see.
Sure. Yes, I can. Might need to just reopen it.
Can you scroll through some of the other things?
It's just it's a bit hard to do this so zoomed in. That's yeah, that's better, right? Okay, so now I'm just going to go through the script and show you how this works. So I'm just going to run the library calls on the patient level prediction and the Strategos package, which hopefully are installed. We're going to set our global seed. Might play around with changing the seed later in one of the exercises. And then you need to point to your database. So in this case, database is just right here. It's in the current directory. And in this synthetic database, like usually when you need to specify the schemas where your data is. So you need to specify the CDM schema where the CDM is, and then you need to specify a working schema where you would create your cohorts, and you need to have right access to this working schema. So in the example database, the CDM schema is in the main schema, and the work schema is called cohorts, and then we're going to use cohort table as our cohort table name. Just going to execute these three. And then we're going to load our cohorts. So in this example, we have a target and an outcome cohort. So this is actually from an ongoing network study where I'm looking at performance of prediction models in the COVID pandemic. I actually have a poster and we want to check it out later. So the target cohort is just diagnosis of COVID, and the outcome cohort is hospitalization because of pneumonia. So these are actual cohorts that have been used in studies. And I'm going to just create an empty cohort definition set in cohort generator and load my cohort. And then I'm going to use Strategos now, which is kind of wrap it around cohort generator to create our cohort generator module specification. Like this, you can use this script as a template for your own studies. So it might look a bit complicated now, but you usually just use the same one and you can change a few things. So here is now we can connect it to the tutorial topic actually. Here we have our covariate settings. This is how we define our features. So we usually use a package called feature extraction for that. And for this example, I'm just going to create the default covariate settings. Actually the help doesn't say a lot what's included, but this basically includes a lot of stuff, almost, age groups, gender, race, ethnicity, conditions, drugs, procedures, devices, but of course you can just change this later if you want to just run your own features. I'm not so sure. Oh, okay.
You can view the object it creates if you want to know some of the
Yeah. Yeah, so it has gender, age group, race, ethnicity, index year, condition groups in 2 windows, drug groups, procedure occurrence in 2 windows, devices, measurement ranges. It's has a bunch of stuff, but the synthetic data doesn't have that many features, so we're not going to be drowned in features. The population settings, this is where we define our time at risk. So we are gonna, it's a binary prediction model. We're gonna let's not delete it. We're not gonna require a time at risk, like Jenna talked about. We're gonna allow people to leave to be censored basically without excluding them. And the risk window is gonna be from 1 to 30 days. So we're predicting hospitalization because of pneumonia within a month. Then we have the pre-process settings. So here we define how the fraction by which to remove rare features. So in this case, forgot to create this. But yeah, in this case, we're removing features rarer than, I think, 0.1%. But you can also change this. And then for continuous features, you're normalizing them to have a max value of 1. And you're going to remove redundancy. So if you have features that together cover all of your data, like males and females, it's going to remove one of them. And we're just going to use the default split settings. So it's just 25% test set, 75% training set. Use threefold cross-validation to select the optimal hyperparameters. And we're going to use just the standard L1 logistic regression with our seed. And there are some other options commented out, and you can like play around with them later. I'm going to print a message which model we selected. And then we're going to assemble this into what we call the model design, which is just like a list that holds all of this together. And here we have the target ID and the outcome ID, which is the IDs of our cohorts we generated. So these should correspond to the values we put here. 1 for our target and 2 for our outcome. And then we're going to assemble this into the model specifications for Strategos. And then we're going to assemble our whole analysis specification, again for Strategos. So this is like an object that we can then save to JSON. And that's like a recipe that we can just hand to everyone, to other people, other sites, and they can execute our exact design with our exact cohorts on their own data. And then we're going to define some results folder. There's like in Strategos, there are 2 types. There's the working folder where you can store some intermediate results which are used during the execution. And then there is the results folder which will save this like a CSV files with your final results that you can then upload to a database for sharing. So, we need to tell Strategos how to which schemas are in our database, with which data, the cohort table name, the folders. And incremental false means that we're not going to try to resume an earlier execution. We're going to give Strategos the information about our connection details, and then we're going to just execute. It's generating cohorts, generating the features, downloading the data. It's running some diagnostics that it runs like as part of the PLP, and now it's like developing our model. It's done the train test split. It's running Cyclops, so it's doing the hyperparameter selection now on our training data. It's done with that. And yeah, we have our model. The AUC performance is almost 73%. Yeah, and then there's a bunch of metrics here, like the calibration. The mean predicted risk and the observed risks are pretty close, around 1%. We also have the training set performance and the cross-validation, the best cross-validation performance. And then it's like actually uploading it to a database. And it's finished now, and it took just over a minute total. And then we can point here to our like working directory, and then we can view the Shiny app to explore our results interactively. Go here to prediction, view models. And here you can see our model, and we can see the number of covariates in our model, the number of non-zero covariates, or yeah, actually the number of non-zero covariates is the covariates in our models. And the intercept, I think we can plot the AUC and the AUPRC. And yeah, that's the basic scaffolding for how to develop a prediction model with patient-level prediction and Strategos. So if you go to section 8 of the tutorial, there are, oh sorry, it's in dark mode again. So section 8 has a bunch of exercises. So the first one is just to explore the coefficients of your model, if you manage to fit the model. Then you can change the model, so you can use XGBoost, you can use random forest. And maybe it's good to know that if you go to odyssey.github.io/patient-level-prediction, that's the website of the package. And then you go to the reference, you can see what's in the package. So for example, binary classification models, you can click that and then you can see all the models that are in the package that you can choose. So go back to the tutorial reference. So like I said, exercise 2 is model exploration. You can change the model. You can change exercise 3, change the seed. You can see how it affects the results, and you can maybe ponder a bit why the results are changing, if they're changing. Exercise 4, you can do a network study. You can change something in a design, save the JSON, pass it to someone else and let them execute it and see if that works. That's actually what we do in network studies. And if you want to go deep, you can install deep patient-level prediction, which is like a plugin on top of patient-level prediction, and you can try what we call our default ResNet. So yeah, I hope that's clear, at least like for the baseline, how to develop a prediction model. But the point of this practical session is that you should try it out. So please try to run this on your own and call one of the tutors to help if you're in if you hit any problems. Thank you.
Okay. Hello, everyone. So if I can get your attention. So my name is Yong Chen. I'm going to spend the next 15, 20 minutes with you to talk about federated learning. I heard from Jenna that there's a lot of interest about scaling up the prediction model to multi-sided prediction using federated learning. So I'm a professor of biostatistics and medical informatics at UPenn. So I have been working on this topic for about 10 years, really started the collaboration with OHDSI. OHDSI has been serving as a great motivation and also collaboration, open science community to evaluate and test our method. So I'm going to really talk about this framework. And so we actually have a lot of material on this topic. We really have more than 30 algorithms now implemented in this framework. But today I'm trying to give you just a bite of what has been implemented at the PDA framework, and I hopefully this will give you some key message, get a sense of how do we scale up? And Jason Luo, who is sitting there from Washington, St. Louis, we have been offering like a full-day workshop to walk through those federated learning implementation and software step-by-step walk through with some mimic data over the time. So, but this will give you a taste of this. So PDA, first of all, stands for Privacy Preserving Distributed Algorithm. There's two things, for people who are kind of my age or older than me, they know what PDA stands for, right? Used to be a Palm computer, but now with a smartphone, no one is using PDA. So we kind of adopted this term. The other thing is that when we say privacy preserving, it's really reflecting policy compliance. But one thing I learned from a friend from at Vanderbilt, Brett Merlin, who is actually overseeing this. He's a privacy expert overseeing this all of us data from NIH in terms of privacy. One thing he said, which is very insightful, is that we should never talk about privacy without the context, right? It depends on, when we talk about sharing data, sharing aggregated data, there could be always some critics from computer science as a domain where say, can you add some noise? Can you do some DP, differential privacy, and so on? Let's hold the horse. Let's say, decide which scenario we are sitting, right? If we are talking about, say, between different hospitals in Penn Medicine health system, we wouldn't worry about sharing aggregated data, even some patient-level data, right? So if we talk about OHDSI collaboration, often we have an umbrella protocol where we can share this type of table one type of aggregated information. Of course, in OHDSI, I think we have some truncation rule. If you have some sparse table, we need to truncate the number by 11 or 5, depending on the context. But let's not talk about things like differential privacy or those type of things. I think sometimes it's overcomplicating things. So really, this PDA is emphasizing we are sharing aggregated information to allow multi-site studies. And the PDA OTA is a term stands for over the air. So that's a term I came up with as a time I was driving a Tesla. Tesla has a functionality. You can update the tools over the air. So that's a concept that borrowed from those domain. So I actually have a 2-minute video to actually give you a very quick overview about what the PDA is. So let me play this and see if it can. The sound.
Integrating data from multiple institutes helps researchers obtain more generalizable findings and better statistical power. A great deal of effort has been made to establish distributed research networks to enable multi-institute collaborations. For example, OHDSI's network features more than 500 million patient records from 19 countries around the world. PCoreNet includes more than 68 million patients in the United States, representing dozens of clinical data research networks and patient-powered research networks. In order to enable efficient analytical studies on multi-institutional data while protecting patient-level information, we are developing a set of algorithms which we refer to as PDA, Privacy-Preserving Distributed Algorithms. Our algorithms are communication efficient, which only requires the collaborating sites to send aggregated information to the coordinating site once. PDA only takes 3 steps. First, broadcast the initial value. Second, share aggregated data. And third, synthesize evidence to obtain the final results. So far, we have developed efficient algorithms for the most commonly used models in healthcare studies, with algorithms for modeling binary outcomes, time to event outcomes, and count outcomes. We are expanding our work to many other types of statistical or machine learning models as well. While we develop our algorithms, we keep 4 principles in mind: privacy preservation, accuracy, efficiency, and heterogeneity awareness. We hope you enjoy exploring our website and learning more about PDA as a next-generation data sharing strategy.
So great. I hope that gives you a sense of what we are working on. And so So for the rest of this presentation, I will give you some concrete use cases. So there's one particular term I keep emphasizing is called communication efficiency. So for those of you who attended the morning session about introduction course for OHDSI, I already talked about this concept, but let me just briefly emphasize. So there's a concept of this human in the loop in almost every single OHDSI collaboration because we need to coordinate with people. We do not directly query your friend's data. We query your friend's data through your friend, right? So there's a human in the loop concept. We need to be respectful of your collaborators' time and also be mindful about the difficulty in scheduling, so-called synchronization. There's a concept in computer science in the sense that if you do computer science is specifically in parallel computing, if you are doing parallel computing, some machine is doing harder task, some machine is doing easier task. So if you parallelize your task to 100 different machines, some machine can be very slow in getting your response. And if your algorithm require results returned from every single machine, it will be really dragged toward the last result before the next iteration. So this will really drag the process to be very slow. It's the same reason applied to our collaboration, OHDSI collaboration. Imagine if you are distributing a protocol that you need 3 rounds of communication, right? And then you have 20 data partners. You have to get a result from all the 20 data partners after running your protocol and codes before the second step. And also you need this requirement before you move on to the third step. Then very likely you will have to delay your timeline dramatically. And sometimes some of the data partners have issues harmonizing their data. They could be changing a job, anything. Those are the things, so-called human in the loop, that happen very, very commonly. So the key emphasis for this PDA is that we push our analytic innovation in the way that we only need a data partner to do one task for one round. So basically, we send this algorithm, some protocol to the data partner. And then of course, initially, we need to harmonize the data. That's what the OHDSI really emphasizing about, for reliability and so on. Run some objective diagnosis, right? In the morning, Jason talked about some diagnostic readiness, fitness for the data. When your data set pass those initial screening quality check, then we are going to share this protocol to everyone, and then you run this only once, and then send the result to us. We will not bother you anymore for the second round, the third round. So this way, this type of federated learning will be more scalable because you can set a clear timeline, and you wouldn't need to bother people around again and again. So that's the key distinction between our PDA compared to other federated learning, especially in computer science, which is often iterative, right? So the PDA, there are a number of very popular algorithms like DRMM and ODEL, ADEC, and so on. So I will walk through some of the examples. But another important thing is that we actually spend a lot of resource to build this infrastructure called the PDA OTA. At least at Penn, we spend at least $250,000 to build this free open resource infrastructure to help people to coordinate each project. So this is basically a secure collaboration file manager, project manager. And then you can create your project. You can name your project as, say, GLP-1 comparative study for kidney outcomes. You can ask different people to share their result online. This platform actually help you to track status, whether your collaborator has sent out the result. You can click one button to send an email reminder, and then you can also check the status of the completeness of all the results and so on. So let me play this next video, which is the last video I'm playing. This is a 1-minute video to walk you through about this infrastructure called the PDA OTA. So let me play this again.
Welcome to PDA OTA, Privacy Preserving Distributed Algorithms Over the Air. PDA OTA is a web-based interface for secured sharing of aggregated data for multi-site studies using our privacy-preserving distributed algorithms. PDA OTA is a unified platform that facilitates national and international collaborations requiring aggregated data sharing for collaborative modeling. PDA OTA synchronizes project status, offers cloud-based SFTP, and generates model-specific tasks for streamlined implementations. PDA OTA provides a user-centered platform for two types of users, the project lead and project participants. PDA OTA also allows users to invite participating sites to collaborate, upload aggregated data, track project status, receive automated email notifications, and generates project summaries automatically. To get started, please check out our other videos featuring detailed tutorials for both the project lead and project participants.
Okay, I think the key message here is really about how do we implement this PDA study. So basically, for any federated learning study, you need to have a project lead, just like any other studies, right? You need to have someone appointed as a project lead. You can have more than one project leads who work more closely, but you need to also make sure the data partners are informed, but you don't they do not need to spend as much energy as a project lead, but they need to be responding to some query requests. So let me just show you this platform. So PDA, OTA, this this is the website. People can go there and then create your account, and then in this platform you can actually it has this dashboard generated, and then it has a very nice job done manual and for specific type of federated learning you want to run. And inside this, this is created by my former student, Jessie Tong, who is now assistant professor at Hopkins. She created her favorite avatar. You can have your own avatar, and then you can have a number of projects, and you can name your projects, and then you can also there are trash bins there. You can use this to manage your different projects, right? So, and within each project, so the job done manual for a given federated learning algorithm you plan to run, there will be corresponding workflow. Say many of them only take 1 or 2 rounds of communication. And then for each round, you can track the status of your data partner who agreed to share summary statistics. Like here is you can see the people from Colombia, people from Korean, they agreed. So some of them complete the task, some of them have not. And there's a button you can click to remind your data partner to send the results with a very convenient link. They can click and upload. So again, this is back to my key concept of human in the loop, because we are working with people. And I had an extensive discussion with Jenna and Martin and Patrick. We specifically designed this to force people to manually upload their summary statistics, because this way they can audit, they can review what data they're uploading. Can we make this automatic? We can, of course, we can automate this process. Even in R, you can have a one button click, it will send it to some job box or something. But this way, this is, I have to quote, privacy is something, is a process, it cannot be reversed. If you share, unintentionally share some patient level information, unintentionally, then this process cannot be undo, right? So we specifically designed this workflow so that people can look at what data they are sharing. Usually it's a very small number, like a predictive model, maybe 200 predictors. You only need 200 numbers in that particular algorithm. So you can review this number. You will have a sense to say this, just like a table 1 doesn't contain patient level information. You feel comfortable or get your institutional approval, send it manually. So this is a intentionally designed process to safeguard against potential safety leak. Okay. Any questions before I get into the use cases? Okay. Okay. Or otherwise, I can go to quickly some use cases. So the first use case is this is actually the very first the OHDSI international study we did with together working with Jenna very closely, led by Chongliang Luo. We have a linear model. So it's very simple. It's a linear model to quantify the risk factor for the endpoint of length of stay. During pandemic, we want to understand what risk factors are impacting the length of stay using an international study. And since this study involves multiple really very different hospitals, including one hospital in Barcelona, one hospital in Korea, and multiple hospitals in East Coast and West Coast. So it's important to think about the heterogeneity. We actually allow the hospital to have very different baseline profile, right? So this way, we actually use this model called the linear mixed effect model. So mixed effect model is an extension of a linear model by allowing site-specific effect to be a random effect. So it's a very popular hierarchical model in statistics. So this DLMM algorithm is a really elegant algorithm to do this federation. The beauty of this is that it's actually going to only require a data partner to share summary statistics only once. So what we did was we actually developed a protocol. I think Jenna was taking the lead developing the protocol, OHDSI protocol. We post this in the OHDSI forum, and we tell them we have a month for you to decide whether you want to join this study. If you have any question, email me directly, and then at the end of the 4 weeks, the month, then we actually recruited 12 sites who agreed to share summary statistics data with us. And later, this led to a paper published at the Nature Communication. So that's one study. I think the strength of this federated learning, other than, in addition to bigger sample size, more generalizable finding, we were able to quantify the heterogeneity across sites. For example, in this particular study, we found that the results, we found the Korean site in particular, their length of stay, even baseline length of stay outcome is much longer than other places. And turns out Korea has a different discharge criterion compared to many other hospitals. So those are the unique insights you can gain from this federated learning. Another paper study we did is also using multiple countries' data to quantify the hospital quality outcome. Like this is another study we did, also called the DGEM study. And normally we need to develop a GitHub page to explain the research protocol and allow people to comment. And this is a more recently published paper at Nature Digital Medicine. We actually figured out a way to fit logistic regression and almost all kinds of generalized linear model with only one communication, and it's also guaranteed to be lossless. And we use this study to quantify the key factors associated with the COVID-related mortality. And this is another Nature Digital Medicine paper published recently in the OHDSI collaboration. And this is an extension of this model by allowing different data sites to have some heterogeneity. So, and finally, this is a federated modified Poisson regression. So I need to make one quick comment about Poisson regression. A lot of time when you have a binary outcome, say yes or no, you have this condition or yes or no, a lot of people we are thinking, oh, let's use logistic regression. So it turns out that logistic regression will give you some estimate called the odds ratio, right? Odds ratio actually do not have as good interpretation as relative risk or risk ratio. If you are familiar with the causal inference literature, there's some concept called the collapsibility. Odds ratio is not collapsible in the sense that if you compare these two subgroups versus some other subgroups. So if you play with the different marginal distribution of subgroups, the interpretation will be messed up. So relative risk is actually more intuitive summary. For that reason, people start to, especially in epi, people start to recommend people use Poisson regression to fit binary outcome. So there's a paper published at AJE, American Journal of Epidemiology, talking about how to use Poisson regression to fit binary outcome. So this is a federated version called ODEP. P stands for Poisson regression. And very concretely, how do we run the federated analysis? As I said before, in the OHDSI forum, you just need to develop a protocol. So let me put it here. So at the beginning, you need to develop a protocol. And we actually, for this study, we work with Jenna very closely. And then we give 1 month window to recruit additional 11 sites. And then for this project, we actually have 2 rounds communication. We give people 1 month for each round to get the results. And normally that will entail some kickoff meeting to go over the protocol, do some Q&A. And then some people will send you some information, say there are some bugs and some particular data-related problem related to their data set. So this is a task from, this is really what the lead site should do. So lead site is in charge of helping with the debugging, refining the process. And then after implementation, as a team, we can meet and discuss interpretation of the results. And usually this is what the study protocol is about. So it's OHDSI study, and then so it's called a DGM study for quality outcome. And then we need to develop a list of variables and study design. All of this need to be listed carefully. So in terms of the type of data to be shared, this is another screenshot. So usually our R package called the PDA automatically handles this. But in case you are curious about what is actually shared, so for this Columbia data, which has more than 5 million patients, covering more than 5 million patients, you only need to share a small file, a JSON file like this. A JSON file will tell you how to correct your model or update your model. It's really sharing a minimal amount of information. So yeah, I think that's all from me. Any questions or comments? So, yeah.
So you didn't talk about what is exactly being communicated. Are you just passing gradients and accumulating it and again updating the model?
Yeah.
At the end?
So yeah, what it looks like is like this. But depending on the algorithm, for linear mixed model, we are communicating a P by P matrix. P is the number of predictors. So to say 200 predictor, we are communicating a 200 times 200 matrix. And for federated logistic regression or federated Cox proportional hazard model, we are sharing some gradient information. So it's better algorithm than meta-analysis. Yeah.
Is one pass usually is enough to update it? I know these are simpler models, but I'm just checking.
Yeah.
Even one pass fixes. Yeah. Okay.
So, yeah, very good question. So the answer is always it depends, right? Depends on how complicated the model is. For linear mixed model, one pass, in the Nature Communication paper, we showed is not only one round is enough, but it's lossless, meaning that you get identical results compared to the pooled data analysis, which will take months to go through the DUA, data usage agreement. For logistic regression model, because it's non-linear model, so one round of communication turns out to give you very close answer because a number of models, they are highly convex. So one step, it can give you very good results. But if you have more complex models, say you want to run a SVM, support vector machine, quantile regression, so then we need to have a separate conversation. So that will be more complicated. So.
There's some risk for like PHI information can be part of the weight and share back to the master or global model. How do you handle that risk?
So what do you mean by so PHI information? For example, the age, right, is a PHI information, right? But this is talking about the aggregated information. So when we, for example, the age, if you think about the DLMM algorithm that I talked very briefly, this algorithm, what you are sharing, suppose you are fitting this DLM, suppose the outcome is say a glucose level, and then predictor is age. So then what you are sharing is basically aggregated data, X transpose times Y. So meaning that it's basically the summation or the inner product of the column for the weights, and the inner product, and then the one vector column for the A1C glucose level, which is a scalar. So that wouldn't be worry about. So
what about like NLP, like clinical notes, that type of AI algorithms?
Yeah, the feature, good question. The feature can be NLP extracted some entity. Those can be some coded. For example, you can use word to vec. You can have certain NLP extracted feature. But again, everything here is a summation or averaging over subjects. So meaning the more subject you have, you actually have more protection against the privacy. So it's all aggregated. That's what we mean. So yeah. So just one last comment. So Jenna and I, we are thinking of launching a monthly working group meeting. So the time will be to be decided, but it will be a week after the PLP meeting, right? So we will be holding those monthly working group meeting, talking about federated learning. I think the best way of learning this is by doing this. We can start with some toy study. So we can have a simple cohort, for example, of general interest. For example, comparing some drugs, GLP-1 versus DPP-4 as an example, right? And then we can look into, say, some cardiac outcomes, say heart failure or hair loss. That's something of general interest. Then we can launch this, multi-site study, and that's one thing we can ensure is that this type of paper will definitely be publishable. So everyone gets opportunity to play with this algorithm. You learn how to run federated learning, and everyone will be part of a publishable paper. So we will follow up with more information. So yeah, thank you.
So thank you all for attending today. Just going to have a quick closing, because I know some of you are probably very tired from a long day. So what did we do today? We started off with a helicopter. Now we've got the PLP dance. What you've learned, you learned how to think of a prediction question that would have clinical meaningness. You then designed the model for that. You then saw from EIC how to actually implement that with R code. And the question is, where do you go next? Well, we've got lots of resources. So if you're interested in using the R package more, we've got the GitHub repo there. If you want to read more about the framework, we've got the Book of Odyssey. And if you want to actually start running some prediction models, we've got our study results and a Odyssey studies repo where you can actually create a network study. So what I'm hoping is that the models and the tasks that you designed, you can actually now start to develop those and actually come up with some clinically meaningful prediction models. So anyone who wants to take their design to implementation, please feel free to reach out, and we can start to actually get those run and potentially even create a network study. And hopefully maybe some of you will actually get publications from that. If you're interested in joining more regularly with this community, we have monthly work group meetings for prediction. So Young mentioned that we're going to have the federated learning one a week after the patient prediction. The patient prediction meets on the first Wednesday of each month at 9 a.m. Eastern Time. So if you're interested in coding or doing research in prediction or anything based on prediction that you've noticed that we do in this community, come join us and we can chat. We have presentations on different topics in prediction, and we just discuss research that we want to start working on. There's also the Odyssey forum, so forums.odyssey.org. You can go there and ask questions and see if anyone's interested in similar research to you. And then if you want to become a developer, so you saw that we have our repo on GitHub. We always encourage people to come and code and contribute. So anyone who wants to add code to that, again, reach out and we'll help you get involved in that. So continuation of the PLP journal, we want to scale everything up as always. You saw that we've done some best practice research. We want to do more of that. So there's plenty of methods research to be done. The ones that I think is the most interesting are the deep learning, the federated, the transfer learning. So I think there's a lot of stuff we can be doing in Odyssey for that. And then there's also the important question, how do we actually assess impact? So let's get models being used and actually assess whether they're working and try and improve healthcare. There's also more development on the methods. So there's always going to be methods development. And so that's always going to be an area for people to contribute. We'd love to hear feedback for how things went today. So what you enjoyed, what you didn't like, what you think we could do better next time. We're going to be sending an email out to ask for feedback. So there should be an email in the next 24 hours. So if you have any comments, that would be great to hear. And then thank you for coming. Thank you for being active participants. And if you have any questions, that's my email address, so feel free to email me. I emailed a lot of you. Most of you got an email for the tutorial, so it's the same email. So you can always just respond to me on that as well. Well, thank you for coming.